Come along as we explore some of the most peculiar celestial bodies in the cosmos, including giant bubbles in our galaxy, nearly empty spaces, and objects that appear to defy the laws of physics. These out-of-the-ordinary features test our knowledge and shed light on the cosmos in novel ways. PSRJ 1748 2446 is the fastest spinning pulsar in the known universe. The Whirlpool Star, or PSRJ 1748 2446 AD, is a star that defies our expectations. It is the fastest spinning pulsar ever found, spinning an incredible 716 times per second, faster than the blades of a helicopter. The Whirlpool Star's extraordinary speed begs intriguing questions about the forces acting in the cosmos, and it is undeniably one of the most remarkable objects in space. To fully grasp their mysteries, however, we must first. Pulsars, a type of neutron star, are the remnants of supernova explosions. These dense cores, which are about 20 kilometers across, roughly the size of a small city, pack more mass than the sun into an area of almost unimaginable density. A sugar cube-sized piece of neutron star material would weigh around 1 billion tons. Pulsars are unique because as they spin, they emit radiation beams, similar to how a lighthouse sends out beams of light. It is located in the Turin 5 globular cluster, a dense grouping of stars that includes some of the oldest stars in the universe. What makes this pulsar truly unique is its incredible spin rate. It rotates 716 times per second, which is far faster than any other pulsar discovered so far. If Earth spun that fast, one day would last less than a millisecond. The name pulsar comes from the pulse of radio waves it emits. The Whirlpool Star is about 18,000 light-years away from Earth in this cluster. The Whirlpool Star's incredible spin rate is not an accident. Pulsars can accelerate through a process known as spin-up. This occurs when matter from nearby stars falls on a pulsar, and as it spirals toward the pulsar, it transfers energy, causing the pulsar to spin faster. The question then becomes, how can a pulsar that spins so rapidly remain intact without rupturing? The answer is the intense gravity of neutron stars. Pulsars like the Whirlpool Star provide valuable insights into the harsh conditions in space because neutron stars have some of the strongest gravitational forces in the universe. Normally, centrifugal forces would tear apart neutron stars as they spin, but scientists think the Whirlpool Star is getting close to the breakup limit, the fastest a neutron star can spin before breaking apart. Additionally, the Turin 5 globular cluster is worth noting for its high concentration of pulses. This makes it an ideal location for studying these objects. The high density of stars in the cluster is probably to blame for the abundance of pulses. In such environments, stars interact more frequently, which can trigger the spin-up process. Or put another way, the dense surroundings of Turin 5 create the ideal conditions for the formation of millisecond pulsars, such as the Whirlpool Star. Thanks to technological advancements, radio telescopes like Australia's Parkes Radio Telescope are able to detect pulsars, which are very rapidly spinning objects like the Whirlpool Star. By meticulously measuring the timing of these pulses, astronomers can determine the exact spin rate of the pulsar. These observations do more than just provide cool facts. They also enable scientists to test some of the most basic theories in. Pulsars, such as the Whirlpool Star, offer a unique opportunity to test Einstein's theory of general relativity in extremely harsh environments. Scientists use the Whirlpool Star's speed as a tool to push the limits of what is known as particle physics in these kinds of environments. They can study matter's behavior under tremendous pressure and the effects of gravity in ways that are impossible on Earth. This pulsar serves as a reminder of the importance of pulsar research in general. Pulsars like the Whirlpool Star allow scientists to probe basic questions about the cosmos, and future technology, like the Square Kilometer Array SKA, has the potential to uncover even faster pulses. This, in turn, could lead to new insights into the most extreme conditions in the universe, and, who knows, maybe even the nature of matter itself. The most hostile settings conceivable ranging from powerful gravitational fields to extremely dense matter, as we have discovered through studying phenomena such as the brightest quasar, where supermassive black holes generate energy jets, and Sagittarius A*, the galactic center, studying the whirlpool star provides a glimpse into the workings of the universe on a cosmic scale. Complete view of the universe. What's so fascinating about the whirlpool star is that it challenges our current understanding of what's possible. As astronomers keep an eye on these rapidly spinning stars, they may discover more pulsars like Sagittarius A, the supermassive black hole at the center of our Milky Way galaxy. One of the most significant objects in our galaxy, having a mass 1 million times that of the Sun, is a black hole. But what is a black hole, and how do we find this invisible giant at the center of our galaxy? A black hole is an area in space where the gravity is so strong that not even light can escape. Black holes form when large stars collapse under their own weight, creating a dense point called a singularity. The area around a singularity is called an event horizon, and beyond it is the boundary of space. Nothing can stop a black hole from warping space and time and testing the boundaries of what is physically possible. Scientists have never had a better chance to study such extreme environments than with Sagittarius A, a supermassive black hole that is millions or even billions of times heavier than our Sun. Situated at the center of the Milky Way, approximately 26,000 light-years away from Earth, Sagittarius A is surprisingly silent compared to other black holes. SG is a type of massive star that has been observed by astronomers using telescopes to study stars in the vicinity of the Milky Way for decades, and they have noticed the extremely fast orbits of these stars, which led them to conclude that SG exists. Despite its dormant phase, SG's gravity continues to dominate the galactic center and control the motion of stars and gas in the surrounding area. Around an invisible object, SG, the strength of its gravitational pull can only be explained by a supermassive black hole. One prominent star in this area, S2, completes an orbit around SG every 16 years, bringing it dangerously close to the black hole so scientists can study its effects. Another star, S62, has an even faster orbit, taking just 99 years to complete one full revolution around the black hole, further confirming its existence in 2022. Though the image may appear blurry, it was a groundbreaking achievement that provided critical evidence of SG's existence and shed light on how matter behaves near the event horizon. Contrary to popular belief, SG is not currently devouring large amounts of material black holes like it plays in vital function in the development of galaxies during their active phases. Supermassive black holes release bursts of energy called jets. These jets can alter the structure of the galaxy and the rate at which stars are formed, effectively acting as a cosmic regulator. Despite its tremendous power, SG does not pose a threat to Earth because we are located 26,000 light-years away, and even the stars that are closest to the black hole are in stable orbits. Instead, SG suggests the Milky Way's galactic center is a dense area packed with stars in varying stages of life, some young and hot, and others older and nearing the end of their cycles. Massive clouds of gas and dust also populate this region, some of which are extremely dense and provide a unique window into the mysteries of the universe, allowing scientists to study gravity, space, and time, which might eventually collapse to create new stars. All of these objects are impacted by the gravitational pull of SG, which shapes their orbits and movement. Although SG is currently silent, it holds the key to understanding how supermassive black holes shape the universe. The story is far from over, and as our technology improves, the secrets of this cosmic heavyweight will become clearer. By studying SG, we gain knowledge about black holes and the forces that have shaped galaxies, such as 3C273, discovered in 1963, stands out as the brightest quasar visible from Earth. This extraordinary object, which is located in the constellation Virgo about 24 billion light-years away, has been a part of our Milky Way since the beginning of time. What is AZA, and why does 3C273, also known as the cosmic lighthouse, hold such a considerable amount of importance? In the annals of astronomy, in order to decipher the cosmic lighthouse, one must first investigate the meaning of the acronym ASA, which stands for quasi. A stellar radio source is an incredibly active object situated at the galactic core, driven by a supermassive black hole. As material, such as gas and dust, spirals towards the black hole, it undergoes tremendous heating, releasing an abundance of energy that spans the entire electromagnetic spectrum. This energy can illuminate entire galaxies and the cosmic lighthouse. Cosmological lighthouse is 4 trillion times brighter than the sun. But what really sets it apart is its historical significance as the first known quasar, which marked a watershed moment in our knowledge of the cosmos. In the early 1960s, astronomers noticed radio signals emanating from objects that looked like stars, but they were too strong to have been caused by regular stars. The breakthrough came when Martin Schmidt and his colleagues found that the light was actually the cosmic lighthouse. Even though it's more than 2 billion light-years away, the cosmic lighthouse can still be seen through telescopes due to its incredibly bright core, which is a supermassive black hole that's constantly devouring matter around it and creating tremendous amounts of energy. This red shift indicates that the object is rapidly receding from Earth, and the cosmic lighthouse is now located far outside our galaxy, rather than just another star. The cosmic lighthouse is an essential tool for astronomers studying faraway galaxies and the early universe. Its brightness facilitates the mapping of large-scale structures in the cosmos, which helps us understand the distribution of galaxies across space. The red shift, which occurs when light stretches to longer wavelengths as an object moves away from us due to the expansion of the universe, is a groundbreaking discovery. The high red shift of the cosmic lighthouse. Because of the cosmic lighthouse, we now know that K-Earths are extremely distant, powerful objects that lie outside of our galaxy. Prior to this discovery, many people thought the universe was quite small, but after seeing K-Earths, we realized that there are powerful, faraway objects outside of our galaxy. This discovery led to the discovery of thousands of other. Each quasar provides fresh information about supermassive black hole behavior and galaxy formation. The cosmic lighthouse is a celestial wonder, but it's also a window into the early universe. Scientists can learn more about the formation and evolution of galactic centers by studying quasars like this one. Quasars are like cosmic lighthouses. They help us map space and understand the universe's large-scale structure. K-Earths-like. The cosmic lighthouse has long fascinated science fiction fans, who often imagine it as a mysterious and powerful object. Although the lighthouse itself doesn't appear in many stories, the concept of quasars has inspired countless depictions of extreme cosmic phenomena. One such object is PSRB 1257+2, also known as the Lich Pulsar. It's absolutely breathtaking with its own planetary system. Located approximately 2,300 light-years away in the constellation of Ver, there are planets in orbit around a pulsar. This discovery, made in the early 1990s, was significant not only because it was the first discovery of planets outside of our solar system, but also because it raised the question of how planets could survive around a dead star, particularly one as extreme as a pulsar. To review, a pulsar is a neutron star that forms when a massive star collapses following a supernova explosion. The Lich Pulsar is unique among cosmic objects because of the planets that orbit it, ranging in size from slightly smaller than Earth to slightly larger. However, the similarities between these planets and our home planet end there. Picture yourself standing on one of these faraway worlds instead of a warm, fuzzy Earth. No atmosphere, no protection from radiation, just continuous exposure to the intense energy of the pulsar. The real mystery, though, is how these planets came to be. When you look at a tiny, rapidly spinning point of light like our sun, solar flares, which are powerful bursts of radiation, would appear mild in contrast to the continuous streams of deadly particles emanating from the pulsar's powerful magnetic field. Considering that pulsars are formed when stars explode in supernova explosions, which would normally wipe out any planets in their vicinity, The question becomes how these planets survived or how they came to be. Two major theories propose different explanations. One holds that the planets are second-generation planets created from the remnants of the explosion. In this view, the materials needed to construct the planets around the pulsar came from the remnants of the supernova. The second theory proposes an alternative explanation. It's possible that the planets were already there before the explosion and somehow managed to survive the tremendous forces of the supernova. Whichever way you look at it, the Lich Owl demonstrates that planetary systems can form or persist in unexpected locations. It also makes us wonder how prevalent planetary systems actually are in the cosmos. If planets can coexist with something as intense and hostile as a pulsar, then maybe there are other surprising planetary systems waiting to be discovered. Let's examine them. There are 3 planets in orbit around the Lich pulsar. Planets 1257 plus 12b and c are similar in size to Earth, but they orbit much closer to the pulsar. Their distance from the pulsar is comparable to Mercury's orbit around the Sun. Despite their size, these planets are dead rocky worlds without atmospheres because of the constant radiation from the pulsar. The smallest planet, PSRB 1257 plus 12a, is about the size of our Moon and orbits even closer to the pulsar, exposing it to even more extreme conditions. The discovering these planets was made possible through a technique called pulsar timing. This method measures the minute changes in the pulsar's spin caused by the gravitational pull of the planets in orbit. By observing these timing variations, scientists were able to detect these planets. This discovery was a game-changer in the search for exoplanets and paved the way for the discovery of many more planets outside our solar system. In the years that followed, planets around pulsars like the Lich pulsar were also discovered. The planets of the Lich pulsar show that planets can exist around all kinds of stars, even those that have already died and turned into neutron stars. This finding deepened our understanding of how planetary systems form and evolve and expanded our thinking about where we might find planets in the universe. Previously, most efforts to find exoplanets focused on stars that were more like our Sun. An important question raised by Lich pulsar is whether or not life could ever exist on these planets. The surface conditions are extremely unsuitable for life as we know it, with constant radiation, no atmosphere, and extremely high temperatures. However, some scientists have speculated that life could exist underground, protected from the pulses of radiation. On Earth, we have discovered life thriving in some of the most extreme environments imaginable, like deep-sea hydrothermal vents and radioactive waste zones. This pulsar system demonstrates that the cosmos is teeming with surprises, from planets orbiting dead stars to the discovery of the brightest quasar. Planets like the Lich pulsar and its companions complicate our understanding of the diversity of life in the universe, as do other peculiar cosmic objects such as the Bout's Void and the Sagittarius A*. Planets in the universe. The Lich pulsar's planetary system stands out due to its extreme and unusual nature. As our understanding of this and similar systems grows, we could uncover even more peculiar and surprising locations with planets, perhaps in settings that seem inconceivable. Perhaps there are other pulses in the universe with planets yet to be found. The Lich pulsar serves as a reminder of this. After delving into the peculiar planets orbiting pulsars like PSRB 1257 plus 2, let's take a leap into something even more extreme. The cosmic cannon, a magnetar situated approximately 50,000 light-years away in the Sagittarius constellation. This particular magnetar is not your average magnetar. It holds the esteemed title of highest magnetic field strength in the universe. Pulsars are intense, but magnetars like the cosmic cannon, which have a magnetic field a quadrillion times stronger than Earth's, really push the envelope. Before we dive into what makes the cosmic cannon so remarkable, let's define magnetars. Neutron stars are already very dense remnants of massive stars that have exploded in supernova explosions, but magnetars have incredibly strong magnetic fields. The gravitational pull of a massive magnetar like the cosmic cannon is so strong that it would distort your very atoms, rendering your biological processes impossible. Even at a distance of 100,000 megahertz, the magnetic field of the cosmic cannon would be enough to erase all of the data from every credit card in the world. But that's not all. The cosmic cannon is renowned for generating one of the most powerful bursts of energy ever detected. 50,000 light-years away, on December 27, 2004, a star unleashed a massive gamma-ray burst that briefly disrupted Earth's atmosphere and even affected the ionosphere. This star's burst released more energy in that fraction of a second than our sun generates in 100,000 years. Now think about how devastating it would have been if this star had been closer, even just 10 light-years away, to strip Earth's atmosphere of all its protective layers, thereby ending life as we know it. Star quakes, which are basically surface shifts or cracks caused by the immense magnetic forces of a magnetar, are the source of the energy released by objects like the cosmic cannon. When these quakes occur, they release gamma rays and X-rays, which are among the most energetic forms of light known to science. The 2004 burst from the cosmic cannon provided scientists with a once-in-a-lifetime chance to study the power of magnetars and raise questions that persist to this day, such as whether or not a similar burst could happen much closer to Earth. If this is the case, the resulting catastrophic event would be similar to pulsar magnetars, which are formed from neutron stars, which are composed primarily of neutrons, and which are left behind after a supernova explosion. Scientists believe that magneta are born when the original star spins extremely fast as it collapses, producing an extremely powerful magnetic field. However, not every neutron star evolves into a magnetar, and this phenomenon is a component of. The cosmic cannon is still in its highly active phase, which is why it continues to emit powerful bursts and magnetic fields, unlike regular neutron stars or pulsars, which can spin and emit radiation for billions of years. Instead, magnetars like the cosmic cannon tend to remain active for about 10,000 years before they settle down and become more like regular neutron stars. The 2004 event was more than just a thrilling energy explosion. It provided a glimpse into the workings of some of the universe's most powerful forces. Similar to how the finding of planets near PSRB 1257+12 broadened our conception of the regions where planets can generate magnetar fields, the cosmic cannon force has prompted us to re-evaluate the boundaries of stellar magnetic fields and cosmic energy. Astronomers and cosmologists study these unusual occurrences in the hopes of better comprehending the operation of these massive stars, and ultimately, it's hard to imagine anything surviving around a magnetar like the cosmic cannon. The combination of extreme radiation, high-energy bursts, and extremely strong magnetic forces would render any nearby planets completely inhospitable. Therefore, the question of whether any form of life could survive in these harsh environments on the planets orbiting PSRB 1257+2 remains an open question. Although it may seem far-fetched, we have learned not to rule out the possibility of life in the universe. The cosmic cannon and other magnetars show how diverse and extreme cosmic objects can be, from gamma-ray bursts strong enough to impact planets light years away to magnetic forces that. This discovery, like the strange pulsoplanets of PSRB 1257+2, challenges our understanding of planetary systems. Similarly, the cosmic cannon challenges our concept of stellar remnants and the forces they can unleash. The immense power of the cosmic cannon raises new questions with each new discovery. Could another gamma ray strike the universe? Could a burst as powerful as the one in 2004 be on the horizon? What if it were to occur closer to Earth? While the answers may not provide comfort, they do keep us on the edge of our seats, wondering about other extreme forces in the universe. One such star is U-78, a hypervelocity star. It's not just that it's 30,000 light-years away from Earth in the Centaurus constellation. Its speed is truly mind-boggling. The average speed of a star in our galaxy is about 4 kilometers per second, but one in the Milky Way is hurtling through space at a whopping 1,200 kilometers per second. We need to investigate the origins of hypervelocity stars like our 78, which travel at incredible speeds, 3 million kilometers per hour, in order to comprehend what causes stars to travel so quickly. Hypervelocity stars aren't born this fast. Rather, they're frequently the product of intense and, in the case of Uranus 78, violent cosmic events are likely to begin with its orbiting another star. This type of binary system, in which two stars are gravitationally locked in an orbit around each other, is common in the universe. However, this binary did not end ordinarily. As the two stars dance around each other, they probably got too close to a supermassive black hole, particularly the gigantic ones at the centers of galaxies like Sagittarius A and Asterisk in Milky Way. As a star approaches Earth, its immense gravitational pull can either shatter it into fragments or, as in the case of a 78, send it hurtling into space at incredible speeds. This phenomenon, called a gravitational slingshot, is likely responsible for sending a 78 hurtling across the galaxy. Imagine a slingshot used to launch a pebble. As the tension builds up, the pebble is released at high speed, following the same principle as a 78, but on a much larger scale. Instead of being flung a few meters, we are catapulted into the universe at 1,200 kilometers per second. It's as if the black hole unleashed a cosmic slingshot and propelled the star into space. The immense hypervelocity that the star achieved as a result of this encounter makes it an important object for astronomers to study because it sheds light on the fascinating dynamics between stars and supermassive black holes, where the effects of gravity distort space and time. What makes a 78 so interesting is that, unlike stars bound to the Milky Way by its gravitational pull, it is still moving away from us. This means that a 708 is probably on a one-way trip out of the galaxy and won't slow down anytime soon. In fact, it is expected to escape the Milky Way entirely, becoming a nomad star drifting alone through intergalactic space. It's a remarkable fate for any star that escapes the pull of an entire galaxy and travels alone through the vast emptiness between galaxies. But how did astronomers first notice it? Uncover Us 78. In 2005, during the Sloan Digital Sky Survey, the star was first discovered. What made it stand out was its unusual speed. It was moving at a rate no star had ever been seen before. As scientists continued to observe, they realized that this wasn't just any fast star. It was one of the fastest ever recorded. Hypervelocity stars like a 78 are rare, but extremely valuable for science because they allow astronomers to better understand how stars form and evolve. We can learn more about the Milky Way's dynamics and the forces at work by studying stars like a 78. One example is the study of black holes, particularly the supermassive ones that lurk in galaxy centers. If a star like a 78 can be flung across space by a black hole's gravity, it demonstrates how powerful and far-reaching these forces are. On the other hand, studying stars at such high speeds raises more questions about what happens to them after they're ejected from their galaxies. A 78 may have an eternal journey ahead of her. As it recedes from the Milky Way, it may continue to wander through intergalactic space, forever abandoning its home galaxy. What's even more fascinating is that there might be other hypervelocity stars like a 78 on similar paths, hurled out of their own galaxies by the violent forces of black holes. Hypervelocity stars also aid astronomers in studying the structure of the universe. By studying stars like a 78, they can gain a better understanding of how massive objects within galaxies shape and influence their respective galaxies. Indeed, black holes are fundamental to galaxy formation. They affect star motion and the structure of galaxies as a whole. Stars like our own 78 are examples of the extreme dynamics that black holes are capable of producing. However, given the size and diversity of the universe, it is not out of the question that there may be other hypervelocity stars out there that are even faster. If found, these stars could provide light on hitherto unexplained phenomena. Hypervelocity stars shed light on the extreme conditions that cause galaxies and stars to reach such incredible speeds, which in turn raises questions about the stars and universe's long-term fates. As galaxies change and black holes grow in influence, will more stars be ejected into intergalactic space? What happens to a star when it leaves its home galaxy? We have already explored other extreme objects like pulses, black holes, and supernovae, and A78 adds another layer to our knowledge of cosmic forces. However, pulses symbolize the end of life for some stars, and black holes show the ultimate destruction of matter. Hypervelocity stars show the aftermath of close encounters with these. And scientists are only just starting to delve into these questions about the galaxy. Destructive forces in a sense. A78 is a survivor who narrowly avoided a black hole's grasp, but now must endure the consequences of space travel alone. Now, let's take a closer look at one of the universe's most fascinating objects, Sirius B, a superdense white dwarf. Located in the constellation Canis Major, it may not appear noteworthy at first sight, what with its smaller size and fainter light compared to its more famous companion, Sirius, the brightest star in the night sky. However, don't be fooled by Sirius B's subtle light. In 1844, a German astronomer named Friedrich Bessel observed something strange while studying Sirius A. He noticed that the star had a slight wobble in its movement. Bessel speculated that another unseen object was orbiting Sirius A, and he was correct. This wobble led to the discovery of Sirius B, a white dwarf that was gravitationally pulling on its larger parent. To understand why Sirius B is so intriguing, we must begin with its discovery. It was a groundbreaking event that allowed astronomers to see an object in space not by light, but by gravitational pull, a method that would play a pivotal role in the discovery of numerous other cosmic phenomena. So what exactly is a white dwarf? Well, they're the remains of medium-sized stars like our Sun that have depleted their nuclear fuel. When a star dies, it sheds its outer layers, leaving behind a dense hot core, which is what eventually turns into a white dwarf. Dwarf Sirius B is a prime example of this process. At one point in its life cycle, it was a massive star that was both brighter and larger than it is now. However, as it dwindled in size, it shed its outer layers and became the dense white dwarf that we see today. Speaking of density, it's incredible how densely packed Sirius B is. Despite being about the size of Earth, it is nearly the same mass as our Sun. To put that into perspective, a single star. The surface gravity of Sirius B is 300,000 times stronger than Earth's. Standing on the dwarf star would be like being 70 kilograms heavier than you are on Earth. Almost unfathomably heavy. Looking at Sirius A in all its brightness might make it seem insignificant, but the truth is that long ago, Sirius B was the star that outshone Sirius A before it became. As time went on, Sirius B shrank and shed its outer layers, causing Sirius A to become the brighter of the two. This switch in roles demonstrates how dynamic the universe can be. Stars are always changing, and even the most massive ones could one day become faint remnants like Sirius B. Despite not being heated by nuclear reactions, Sirius B is still extremely hot. Its surface temperature is more than 25,000 degrees Celsius. The star has been cooling for billions of years, retaining heat from its previous life as a red giant. Even though it doesn't produce any new energy, this residual heat keeps it glowing faintly as it cools. Sirius B allows astronomers to study this characteristic of white dwarfs, and its expansion into a white dwarf is one of the most intriguing parts of its history. While transforming into a red giant, Sirius was probably encircled by a planetary nebula, a glowing shell of gas and dust that is the outer layer of a dying star that is ejected into space, leaving behind its dense core. Today, this nebula is long gone, but its memory lives on in the remnants of Sirius. Even though Sirius is nearing the end of its life, astronomers still find its existence incredibly important because they learn more about. Sirius B, a white dwarf, provides a unique window into the future of stars like our Sun, which after billions of years will also cool down and become a white dwarf. By studying Sirius B, we can speculate about what that future might hold. One of the biggest questions about Sirius B is whether or not it has ever been home to planets. Could planets have orbited the star before it turned into a white dwarf? So far, no planets have been found that any planets in Sirius B's orbit may have been destroyed or thrown out of the system when the star exploded into a red giant. This discovery begs the interesting questions. What happened to any planets in other star systems that had planets like Sirius B? Could any planet have survived such a drastic change? As for what the future holds for Sirius, we know that white dwarfs cool down and eventually fade into black dwarfs, which are the icy, dark remnants of stars. But wait, the universe isn't old enough for black dwarfs to exist just yet. White dwarfs like Sirius B won't cool down entirely for billions of years. So even though we can predict Sirius B's future, that future is still a ways off. Sirius B's existence also raises bigger cosmic questions, like how white dwarfs like this one affect the motion of stars and galaxies. In this particular case, Sirius B's gravitational pull causes a small shift in its orbit, which in turn raises some interesting questions about the nature of space and the nature of the universe. Studying Sirius B helps astronomers better understand these dynamics and how galaxies evolve over time. What about its relation to other strange objects in the universe? In previous discussions, we've explored the intense magnetic fields of neutron stars and the tremendous speed of hypervelocity stars like US-78. While these objects might seem vastly different from Sirius B, they all have one thing in common. They all help study the interplay between the visible and invisible parts of the universe. We learn about the universe's extremes through objects like neutron stars, hypervelocity stars, and white dwarfs, which have extremely high densities and speeds. Now, we come to the last question. What happens when two white dwarfs merge? While this won't happen with Sirius A and B, it can result in a spectacular cosmic event called a supernova explosion when the combined mass of the two white dwarfs is large enough. Stars like Sirius B don't ultimately end up in a supernova explosion, but their existence teaches us that such events can happen anywhere in the universe. SN 1998 BW, also known as the Eddington Limit Star, is one of the most spectacular examples of this phenomenon. It wasn't until 1998 that the Eddington Limit Star came to the attention of astronomers. At its core, the star defies traditional limits and sheds light on the mysterious forces at work during the death of massive stars. Supernovae are among the most energetic events known to science, and this was one of the rare instances where the star was almost simultaneously observed with a gamma-ray burst, so the coincidence became a inspiration for a more thorough examination that brings up important concerns regarding the connection between these bursts of energy and the violent death of stars. To fully grasp the uniqueness of the Eddington Limit Star, one must be familiar with the idea of the Eddington luminosity. This is essentially the point at which a star's radiation becomes so strong that it counteracts its own gravitational pull. Once a star surpasses this limit, it can no longer maintain its structure. This supernova was unique in the enormous amount of energy it released, which led to catastrophic explosions and other extreme consequences like mass ejections. The star behind the Eddington Limit was enormous and massive, and it was nearing the end of its life as a result of burning through its fuel. With no energy left to support its core, the star's outer layers were violently ejected into space. Astronomers were taken aback by the brightness of the Eddington Limit Star, which propelled it into the hypernova category. What's more, they discovered that the star released jets of material moving at incredible speeds, which are typically associated with powerful stellar collapses, such as when a star's core implodes and forms a black hole. Despite this, the gamma-ray burst was linked to the Eddington Limit Star. Despite the star's relative weakness, the indisputable link between the two events provided a once-in-a-lifetime chance to study both phenomena simultaneously. The Eddington Limit Star's energy levels were significantly higher than scientists had predicted. Supernovae are already among the most energetic cosmic events, but this one blew them out of the water. At its brightest point, the Eddington Limit Star's luminosity surpassed that of the Eddington luminosity, proving that stars can surpass their theoretical maximum luminosity limits. Based on the data, scientists believe the original star was several times the size of our Sun when it exploded. All that remained was a dense core, which likely collapsed into a black hole after the explosion. Astronomers studied the aftermath of the Eddington Limit Star and gained valuable insights into the type of star that created it. This discovery fueled new research into the collapse of massive stars and how their internal forces can break down in such an explosive fashion. In stellar evolution, the process of a massive star ejecting its outer layers into a black hole is a crucial event. The Eddington Limit Star taught us not only how stars work, but also how they announce their demise. Gamma-ray bursts are cosmic beacons, and a simultaneous occurrence of the two phenomena in the Eddington Limit Star's gamma-ray burst prove that they are related. Granted, not all supernovae produce gamma-ray bursts, but the Eddington Limit Star did. One of the most intriguing aspects of gamma-ray bursts is the relationship between the Eddington luminosity and the Eddington Limit Star. As stars evolve and push the boundaries of their natural limits, they create new pathways for astronomers to understand the universe. The Eddington Limit Star serves as a powerful reminder that even the most established rules in astrophysics, like quantum gravity, can't explain everything. If the conditions are right, the Eddington limit can be broken. The jets of material ejected by the star probably had a significant role in the gamma-ray burst that went along with it. The jets are traveling at almost the speed of light, which is believed to be one reason why gamma bursts are so powerful and energetic. They show us the cosmic forces at work during a star's death, which is a real challenge to our current understanding of physics. The Red Square Nebula and other planetary nebulas, like the Square Nebula, are the remnants of stars that have exhausted their nuclear fuel and ejected their outer layers into space. These nebulas, which are located about 2,000 light-years away in the constellation Scorpius, are among the most visually striking objects in the universe due to their unusual geometric shape. Planet nebulas typically have a spherical or irregular shape due to the gas ejected by dying stars, but the Red Square Nebula looks square or rectangular. However, this is more due to our viewing angle than the nebula's actual shape. The actual structure of the nebula is more diamond or pear-shaped. An optical illusion of a kite-like square is created by the arrangement of gas clouds and the way light passes through them. The unique shape of the nebula is the product of complex forces. As the star sheds its outer layers, its strong magnetic fields and rotational dynamics shape the gas that is ejected, giving the nebula its distinctive appearance. The Red Square Nebula was initially discovered in 2004 with the use of the Very Large Telescope VLT in Chile. Astronomers were able to study a planetary nebula with an unusual shape. Detailed observations showed that the nebula was shaped by the star's intense ultraviolet radiation and magnetic forces, which are responsible for the nebula's distinctive appearance. The star at the center of the Red Square Nebula is a massive white dwarf, which is both hot and instrumental in creating the nebula. The electromagnetic radiation from stars ionizes the gas around them, causing it to glow. This radiation also influences the structure of the nebula, giving it its distinctive patterns. By studying the Red Square Nebula, astronomers gain valuable insights into star life cycles, including how stars die and how their remnants interact with their surroundings. The nebula's unique shape also reveals how magnetic fields shaped the last stages of stellar evolution. Dark energy, the cosmic force driving expansion, was first detected in 1912 when astronomer Vesto Slyer noticed that distant galaxies were redshifted, meaning they were moving away from Earth. This observation was one of the first clues hinting at something strange about the universe. And the Square Nebula structure is a prime example of how cosmic forces interact with one another to create intricate and unexpected shapes. Although its complete significance was not fully grasped at that moment, Slipher's discovery would go on to link to one of the most perplexing ideas in contemporary cosmology: dark energy. Jump ahead to the late 20th century, when astronomers made a breakthrough with the Hubble Space Telescope, studying faraway type A supernovae, and discovered that these exploding stars seemed fainter than expected. This faintness wasn't merely an anomaly. It indicated that the expansion of the universe was accelerating. Astronomers were taken aback when supernovae revealed that the universe was actually expanding at an unprecedented rate, rather than slowing down as previously thought. All the evidence pointed to gravity eventually drawing the universe back together. But these new findings cast doubt on that theory and ushered in a radical change in our view of the cosmos. How can we be sure that dark energy is real? Aside from observations made by supernovae, another important piece of evidence comes from the cosmic microwave background, or CMB. Detailed studies of the cosmic microwave background, CMB, show that the cosmos began expanding and accelerating rate billions of years ago, lending credence to the idea that an unknown force, now called dark energy, is at work. Galaxy clusters, which are enormous structures held together by gravity and contain thousands of galaxies, also contribute to our understanding of dark energy. But the distribution of these clusters across space points to the existence of an opposing force to gravity. Dark energy, it seems, isn't merely expanding the universe. It's also actively hindering the formation of galaxy clusters. In fact, studies have shown that, compared to when gravity was the sole force, galaxy clusters are now more widely spaced. To grasp this concept, consider the universe's large-scale structure, which consists of filaments, clusters, and enormous voids. The Sloan Digital Sky Survey, which has mapped millions of galaxies, has provided key evidence of this expansion, revealing that voids are expanding more rapidly than previously thought. Dark energy's influence goes beyond galaxies and voids. It even impacts time itself. It's not just pulling galaxies apart. It's stretching the very fabric of space, creating more emptiness between cosmic structures. Recent research suggests that as the universe continues to expand, it strains the fabric of space-time, which could be impacting the cosmic scale of time flow. For example, time dilation, which has been observed in faraway supernova remnants, shows that time seems to slow down in regions where dark energy is most prevalent. This finding adds to the mystery of dark energy and suggests that it has a profound influence on the structure of the universe and the flow of time. But dark energy isn't only a factor in the present. It also holds the key to the future of the cosmos. If the present acceleration rate is maintained, galaxies will continue to recede from one another, and cosmic structures will drift out of each other's reach. Stars will die out, and the universe will darken and cool down, creating a scenario that scientists refer to as the Big Freeze. Another, more extreme, possibility is the Big Rip, which suggests that the effects of dark energy could become stronger over time if. In such a scenario, dark energy would not only push galaxies apart, but it could eventually tear them apart as well. Gravity would no longer be able to hold them together, and the universe would be ripped to shreds, leaving behind nothing but an empty void. On the other hand, there is the possibility that dark energy's effects could balance each other out, resulting in a more stable rate of expansion. In this case, galaxies would still be moving apart, but at a slower rate, enabling stars to undergo formation and evolution at a more leisurely pace. Although this future may not be as catastrophic as the Big Bang, it would still result in a universe that gradually becomes more isolated as galaxies move apart. What's intriguing is that, despite its profound effects, our understanding of dark energy remains shrouded in mystery. Could it be an entirely new type of energy, unexplored as science? Or could it symbolize something even more enigmatic, possibly connected to the very nature of space-time? This begs some of the most pressing questions. In contemporary cosmology, and scientists are working feverishly to discover solutions. Current research on dark energy is also pushing the limits of technology. Surveys like the Dark Energy Survey and the soon-to-be-built United Kingdom Large Telescope aim to create a more precise map of the universe than ever before, with the hope of discovering new insights into the workings of dark energy. With these tools, astronomers will be able to study billions of galaxies, painting a clearer picture of the universe's evolution and the role that dark energy has played in that evolution. One example of how dark energy is interconnected with other cosmic phenomena is the phenomenon of hypervelocity stars. These stars are traveling through space at incredible speeds and are typically ejected from galaxies as a result of gravitational interactions. However, the vast void that dark energy creates could allow them to travel even farther and faster. Another example is the bullet cluster, which is evidence of indirect dark energy, since it shows that something is expanding space and making. Hogg's object, also known as the Ring Galaxy, was discovered in 1950 by Arthur Hogg in the constellation of Serpents. At first, he thought it was a planetary nebula, but further examination revealed that it was actually a nearly perfect ring galaxy, which was far more unusual and intriguing. This finding challenged traditional theories about galaxy shapes, which had previously focused on familiar spirals or elliptical shapes. There was a luminous cosmic ring with young blue stars encircling an older yellow core that hung like a cosmic eye in space. What's strangest about Hogg's object is that, contrary to most ring galaxies, it doesn't seem to have a nearby companion galaxy. Usually, rings form when two galaxies interact, drawing gas and stars into these beautiful circular formations. Since no such companion has been discovered, Hogg's object seems to exist alone, which makes its existence all the more perplexing. Distinguish itself even more from other galaxy formations. Its formation might have been far less violent and distinctive than the violent collisions observed in other galaxies. The stars within the ring are among the youngest you'll find in a galaxy. These blue stars are just starting to shine brightly, but they stand in stark contrast to the older yellow core located at the center. This discrepancy in ages further adds to the mystery surrounding the galaxy, suggesting that the outer ring formed after the core had already settled. The formation of a star ring around Hogg's object has long been a mystery. However, the ability of Hubble's Space Telescope to peer so far into space has revealed something else lurking in the galaxy's background, beyond the bright blue stars. There's a faint second ring, barely discernible to all but the most sensitive instruments. This finding suggests that the galaxy may have a more intricate history. I find it particularly intriguing that the core of Hogg's object, despite being surrounded by these energetic young stars, remains remarkably undisturbed. One would expect such contrasting star populations to interact gravitationally, pulling at each other, creating distortions, or even causing, but instead it appears to have gone through multiple stages of formation, with one ring forming long after the other. Or is there an entirely different process at work here, one that we don't fully understand? Starbursts, but none of that is visible here. Instead, the core and the ring seem to coexist peacefully, which begs the question, what is keeping this galaxy stable? The study of ring galaxies relies on optical images, which show the core and ring in stark contrast, allowing astronomers to better map out the distribution of gas and stars within the galaxy. However, spectroscopy is more than just a pretty picture. It's also a method that analyzes the light from different parts of the galaxy to determine its age, chemical composition, and rate of star formation. In the case of Hogg's object, this method reveals a significant disparity in the ages of the stars in the core and the ring, revealing the very different environments within the same galaxy. As astronomers continue to probe the object, they have discovered additional characteristics, puzzles that have so far defied explanation, one of which is the lack of evidence of a recent galactic collision or even a smaller satellite galaxy that could have caused the ring to form. Typically, ring galaxies form when one galaxy passes through another, pulling gas and stars into a ring. However, in this case, there is no sign of either of these dramatic events. Instead, some theories propose that the ring may have formed due to internal instabilities, where portions of the galaxy's matter shifted. Hogg's object stands out from other cosmic structures like the bullet cluster or the immense forces of dark energy, which tell stories of large-scale cosmic violence or the mysterious expansion of the universe, while creating the striking structure we see today. Most ring galaxies have clear backstories about interacting with neighbors or crashing into other galaxies. The universe Hog's object appears to be undergoing a peaceful process, but that doesn't make it any less mysterious. Here's an outlandish idea. What if the ring isn't actually part of Hog's object? Some astronomers have speculated that it could be a galactic illusion, with the ring actually representing a distant galaxy that is perfectly aligned with the core from our perspective. It's a fascinating but implausible theory, and if it's true, it would add another layer of mystery to this already complex structure. Hog's object, with its apparently disconnected parts, shows no signs of the gravitational tug-of-war we'd expect in most galaxies. Usually, distortions or even chaos would be caused by the gravitational forces between the core and the surrounding stars. But in this case, it seems like two unrelated galaxies are actually merging into one. Now, this is all speculation, but it does demonstrate how strange and unpredictable the universe can be. Star Tabby, also known as KY846-2852, is an unusual dimming star that stands out among the outer ring stars. Unlike stars and galaxies that have undergone major collisions or disruptions, the stars in the ring appear to have formed relatively quietly, without the usual cosmic drama. Could this be a sign of an unknown force stabilizing the galaxy, or a new type of galaxy formation process that we haven't fully understood? One of the most mysterious stars ever found, Tabby star has been studied for a long time, but it wasn't until the Kepler Space Telescope began its mission that scientists noticed something really out of the ordinary. Kepler had hoped to find exoplanets by observing how stars dim when planets pass in front of them, but Tabby's star showed dimming events that were both unexpected and deeper than what a planet could explain. What's more, the star's dimming pattern doesn't match In contrast to other stars with exoplanets, Tabby's light dims by as much as 22% on a regular basis. This is incredibly unusual, and what's more perplexing is that the dimming doesn't follow a pattern. Sometimes the star dims for a few days, and other times it stays dim for weeks or months. The lack of a regular cycle makes this mystery all the more intriguing, and it has scientists from all over the globe intrigued by its discovery. Dimming behavior isn't new. Historical records, including those from Harvard's collection dating back to the 19th century, reveal that Tabby's star has been gradually fading for at least the past 100 years. This long-term dimming is unusual in and of itself, suggesting that something ongoing and persistent is affecting the star over time. One of the early theories put forward to explain the strange dimming was that a large cloud of dust was passing between the star and the Earth. While there have been numerous theories put forth, one that garnered significant media attention was the potential existence of an extraterrestrial megastructure, like a Dyson sphere, which would explain the star's decreased brightness. However, this theory soon ran into problems, as dust typically emits infrared radiation, and when astronomers examined Tabby's star with infrared telescopes, they did not detect enough heat to support the existence of such a cloud of dust. Despite widespread speculation, there is currently no evidence to support the idea that a sophisticated civilization constructed a spherical structure to harness energy from a star. The star's inability to emit strong X-ray or ultraviolet radiation, as would be expected in the event of extreme stellar activity. When stars exhibit unusual behavior, it's often because they're experiencing flares or other magnetic events. However, Tabby's star doesn't have any strong X-ray emissions, ruling out common explanations like pulsations or stellar flares, which can explain variations in brightness. An additional finding from the past century is that the star has been gradually dimming, but not in the typical way. Instead, the fading looks gradual and continuous, rather than the sharp drops seen in other stars, caused by objects like planets or comets. This means that Tabby's star is probably going through a unique process that could be caused by more than one thing. Another theory that hasn't gotten much traction, but is intriguing, is that Tabby's star could be eating a smaller companion star or planet. This process, called stellar accretion, could cause unexpected dimming as material falls into the star. The interstellar visitor Oumuamua was initially noticed as it moved through our solar system on an eccentric trajectory, clearly indicating that it originated from beyond our solar system. This behavior was unlike anything astronomers had ever seen before, and it could be explained if the star is gradually absorbing debris from nearby objects. The irregular dimming and lack of typical emissions are other characteristics of dimming stars. The discovery of Oumuamua, the first interstellar visitor, was a watershed moment in the history of scientific knowledge. The object's unusual motion caught scientists off guard, and they soon realized that it wasn't behaving in the usual pattern seen in cosmic objects formed in our solar system. The object's unusual shape and rapid speed further added to the mystery surrounding it, and astronomers soon began to speculate about. This object is unlike anything we've seen before. Most celestial bodies, like asteroids and comets, have round or irregular shapes. However, Oumuamua was noticeably elongated, resembling a giant cigar, and it tumbled through space at an estimated 800 million kilometers per hour, making it one of the longest objects ever recorded. The question is, how did something so unlike anything we normally see end up traveling through our solar system? Some scientists have speculated that Oumuamua's peculiar shape is the result of its unusual trajectory. Oumuamua may have been expelled from a binary star system, where the gravitational forces are more complicated. The intense forces it encountered there likely shaped its shape. One of the most intriguing mysteries about Oumuamua was that it did not have a cometary tail, which is usually formed when a comet approaches the sun and the surface ice melts, creating a bright trail of gas and dust. However, as Oumuamua got closer to the sun, no such tail emerged from the sun, leaving scientists bewildered. One theory suggests that the surface of Oumuamua could have been composed of hydrogen ice. However, this would explain why the object's unexpected movements would not be accompanied by a visible tail, further adding to the mystery surrounding its composition and behavior. Another conundrum emerged when astronomers examined the trajectory of Oumuamua in space, which objects typically follow. Predictable paths dictated by gravity, but Oumuamua appeared to gain speed as it departed the solar system, which wouldn't make sense if it were just coasting on its initial momentum. Some speculated that this additional speed could be caused by outgassing, a process where gases escape from comets and give them a little boost. However, the absence of a tail or other visible gas signs cast doubt on this theory. Another possibility was that it could be due to the pressure exerted by solar radiation or the force of sunlight if Oumuamua, where sunlight could propel it like a sail catching the wind, but no one anticipated such behavior from an object of such peculiar shape and motion. Scientists have also investigated possible origins, with some suggesting it was a fragment of a larger object ejected from its home star system, and others suggesting it originated from the outer edge of an exoplanetary disk, a region comparable to our own Kuiper belt or cloud, where debris settles. The ejection of such a fragment could have happened as a result of large planets migrating in its original system, a process that astronomers believe has influenced the history of our solar system. Another facet of this cosmic mystery is Oumuamua's rotational motion as it traversed our solar system. It wasn't merely moving, it was tumbling end over end. Its peculiar shape and tumbling motion further suggest that Oumuamua had a turbulent past before it came to our spectral region, which is consistent with the idea that it may have originated in a binary star system, where such interactions are more common. Its spinning motion also indicates that it may have been subjected to intense gravitational stress before it arrived here. Further intriguing evidence emerged from the analysis of Oumuamua, suggesting that its surface does not match the composition of any known comet or asteroid from our solar system. The observed reddish tint may be due to space weathering, which involves exposure to cosmic rays and interstellar dust over millions of years. This weathering process could have changed the surface chemistry of Oumuamua, adding to the evidence that it has been traveling through the galaxy for a very long time, possibly millions or even billions of years. While most scientists have dismissed the idea due to a lack of solid evidence, the mere suggestion speaks to the extraordinary, leading some to speculate that Oumuamua might be an alien probe. Its unusual shape, high speed, and unexpected acceleration led some to wonder if it could be a spacecraft sent by an advanced civilization. Despite all the scientific data collected, this theory gained traction in the public eye. Researchers have concluded that the enigmatic FMY bubbles situated above and below the Milky Way center are either naturally occurring or extremely unusual. The lack of any clear indications of artificial construction, such as radio signals or regular maneuvering, has left them perplexed and uncertain about the nature of Oumuamua and other interstellar visitors. Recent studies have suggested that these enormous bubbles may be younger than previously believed, suggesting that they may have formed recently. The existence of these structures, which are relatively young at less than 10 million years old, calls into question long-held beliefs that such structures take hundreds of millions of years to form. One intriguing theory involved an event connected to our galaxy's supermassive black hole, Sagittarius A, which is now quiet but may not have always been. Some scientists propose that the FMY bubbles are remnants of a massive explosion, a bipolar jet from the black hole during periods of intense activity. This black hole may have ejected material in the form of massive bubbles. This finding raises further questions regarding the previously chaotic galactic center. The gamma rays emitted by these structures are just one piece of the puzzle. They also emit non-thermal radio waves, which are generated when high-energy particles interact with them. These waves may indicate the presence of shock waves within the bubbles. X-ray observations have revealed the structure of the bubbles, which adds another layer of mystery to their formation. Scientists have been taken aback by the intense non-thermal radio emissions, which are rarely seen on such a large scale in any galaxy. The polarization of the light from inside the bubbles also sheds light on their magnetic fields, which are chaotic and turbulent rather than simple calm lines. A fascinating discovery involves electron-positron annihilation within the bubbles, which happens when electrons collide with their antimatter counterparts, positrons. This suggests a violent origin, possibly driven by past black hole eruptions or intense bursts of star formation. The shock waves are likely connected to high-energy explosions that happened when the bubbles first formed, giving us a hint of how powerful the processes shaping the Milky Way once were. Researchers have discovered evidence of energy-releasing interactions within the bubbles. These interactions may be associated with the black hole's output or with more exotic physics, such as dark matter. The symmetry of the Fermi bubbles is another peculiarity. They extend nearly perfectly in both directions, which is surprising given the chaotic environment at the galactic center. Their symmetry adds to their mystique, as large features like these typically exhibit distortion, particularly in light of the current activity near the Sagittarius A*. One startling discovery is the unusually strong magnetic fields within the Fermi bubbles. These fields shape the bubbles and influence the movement of particles within them, which in turn affects the path of cosmic rays through the Milky Way. In the midst of galactic chaos, magnetic force may be responsible for maintaining the bubble's symmetry and shape. Speaking of cosmic rays, FMY bubbles could be acting as accelerators for these high-energy particles, which zip across the galaxy at nearly the speed of light. The acceleration of these particles could explain their behavior in our galaxy and beyond. The size, shape, and intensity of our galaxy's bubbles make them stand out, leading scientists to wonder what makes our Milky Way unique. They have also studied similar bubbles in other galaxies, which has helped them understand what makes our Fermi bubbles unique. It has also led them to speculate that the mysteries of dark matter may be connected to our Fermi bubbles. There is currently no conclusive evidence, but some researchers are wondering if the gamma ray emissions from the bubbles could be dark matter annihilation. Dark matter, which comprises a significant portion of the universe but is invisible to the naked eye, could interact in ways that we are only starting to comprehend. If the FMY bubbles are involved in this process, it could provide answers to one of the biggest mysteries in the universe, the Oddities void, a vast cosmic vacuum that spans around 330 million light-years and is among the largest. The known cosmic voids are large areas that are shockingly empty of galaxies compared to their surroundings. These voids were found in 1981 through extensive galaxy surveys, and they show an unusual lack of density in what should have been a denser cosmic area. The Boots void is thought to have originated during cosmic inflation, a period of rapid expansion immediately after the Big Bang, which could explain its formation. Instead of a slow, gradual emptying, the size of the Bota void suggests an imprint left by the early stages of the universe. An interesting feature of the void is its unusual gravitational effects. Light is bent around the void because of its low density, which causes strange observations of faraway cosmic objects. This distortion can shed light on how cosmic voids affect light bending and the distribution of dark matter. Could this be a chance to learn more about the enigmatic nature of the void? The enormous size of the body's void could provide new insights into the interactions between cosmic structures and dark energy, which is speeding up the expansion of the universe. The void also has a major impact on the cosmic web, altering the formation and evolution of large-scale cosmic structures by disrupting the usual distribution of matter and energy. By studying the dynamics of the void and its surroundings, scientists can better understand cosmic voids and their. The Phobos void stands out from other cosmic voids due to its rarity in large-scale structures. Unlike other voids, which often contain galaxy superclusters, the Phobos void is almost entirely devoid of these formations. This supervoid status is further highlighted by its unique lack of galactic content, which makes it stand out in the vast cosmic landscape. Deep field surveys and precise. Researchers have been able to learn more about the structure of the void and its role in the cosmos through the use of galaxy redshift mapping, which has given them a bird's-eye view of the area. One example is gravitational lensing, which helps scientists map dark matter in and around the void by showing how massive objects bend from objects behind them. This technique also sheds light on how dark matter interacts with such large empty spaces, which can help explain its elusive nature. When astronomers initially discovered this massive void, while our understanding of cosmic voids was in its infancy, the Buddhist void's enormous size and the lack of expected cosmic structures in such a large area generated a great deal of interest and discussion. This anomaly called into question long-held beliefs about cosmic voids and led to a reassessment of their place in the cosmos as a whole. What makes the Buddhist void so remarkable is its massive size in addition to the almost total absence of galaxies. The body's void is a prime example of how cosmic voids affect the growth and distribution of galactic structures. As a result, it has become an important part of our understanding of the large-scale organization of the universe, and it stands out from other voids that may contain sparse galactic formations or structures because of its nearly complete lack of matter. This unusual feature has prompted scientists to reevaluate and revise their models of cosmic evolution. The Methuselah star, formerly known as HD 14283, has long piqued the interest of astronomers due to its mystifying age and the clues it provides regarding the early cosmos. Located in the Hydra constellation at a distance of approximately 190,000 light-years, the star is part of an old class of stars known as Population 2 stars. Like other stars in this group, the Methuselah star offers a rare glimpse into the early stages of the universe. What makes the star stand out, however, is its initially estimated age, which appears to have challenged our understanding of. In the past, scientists believed that the universe was around 138 billion years old, but its actual age is closer to 16 billion years. This age discrepancy sparked debates and ultimately led to a reevaluation of the star's age and our cosmic timeline. To find out how old a star is, astronomers use the Hertzsprung-Russell diagram, which plots stars according to brightness and temperature. Older stars usually have fewer heavy elements because they formed before these elements were widely used. The Methuselah star is a low metallicity star, meaning it has fewer of these heavy elements. Its age and low metallicity make it an ancient star, but why? We need to reevaluate our stellar evolution models to figure out what happened to this star. The Methuselah star's brightness and temperature could indicate a different path of evolution than what we thought. This could mean the star is younger than expected, or it is possible that the star's development is more complicated than our models predicted. Another possibility is that the methods used to determine the star's age were inaccurate. However, new technology has allowed for more accurate measurements, which have brought the star's age down to approximately 137 billion years. This new estimate is more in line with the universe's age, clearing up any confusion. Beyond its age, HD 14283 sheds light on the early universe and the formation of galaxies, serving as a model for some of the population 3 stars, the first stars to form from the primordial gas that existed after the Big Bang, were massive and had short lives. They contributed to the formation of galaxies and planetary systems by fusing together heavy elements. Knowledge of this process helps scientists understand the conditions in the cosmos immediately after the Big Bang. Ancient stars like the Methuselah star can teach us a lot about the early universe and how it changed over time. It also links to other cosmic phenomena like the Buddha void and Fermi bubbles, which provide insight into cosmic structures and galactic dynamics, respectively. So, studying the Methuselah star is important because it helps us understand the history of the universe and how stars like it evolved. Scientists study old stars and other celestial objects to better understand the universe's history and how different events have molded it over billions of years. As our understanding of the universe grows, our tools and models also improve, but discoveries like the Methuselah star highlight the need to continue refining our knowledge and exploring new research avenues. Through studying these objects, we gain a better appreciation for the universe's complex processes and astounding design. Now, the question is why the Methuselah star seemed older than the. What does HD 140283 tell us about the formation of the first galaxies? The star's brightness and temperature were used to estimate its age initially, which seemed to suggest it was around 16 billion years old. However, this discrepancy led scientists to revisit the star's characteristics and the methods used to estimate its age. As a result, the revised age is more in line with the universe's age. Studying this star sheds light on the early universe and its conditions, as well as the processes that formed the first galaxies. By studying ancient stars, scientists can learn more about the creation of heavy elements and their role in the development of galaxies and planetary systems. One of the most peculiar and fascinating objects in the universe, Hans Vorp, was found by a Dutch amateur astronomer. In 2007, astronomer Hanny van Arl was poring over data from the Galaxy Zoo project when she came across an object that stood out for both its appearance and the mystery surrounding it. Located approximately 600 to 50 million light-years from Earth, this object is known as Hans Vorp, and it is a massive cloud of gas and dust near the galaxy IC 2497. The object is a part of a larger cosmic mystery that has fascinated scientists and astronomers. The optical light that reaches the cloud is green because of the emission. The lines of doubly ionized oxygen in Hans Vorp give it a striking appearance in space. It is a kind of ionized gas cloud or high region, and what really sets it apart is its peculiar relationship to the nearby galaxy IC 2497. Observations have linked the cloud to an event in the past involving the active nucleus of the galaxy, specifically its central region, which is home to a supermassive black hole that was once actively devouring matter. One of the most fascinating things about Hans Vorp is how it relates to galaxy IC 2497. The cloud looks like it's from a previous AG phase when the black hole emitted powerful radiation that energized the gas and made it emit light. However, current observations show that the nucleus of IC 2497 is no longer in this active phase, so there's a discrepancy between the cloud's brightness and the actual brightness of the galaxy. The present condition of the galaxy has prompted researchers to seek out explanations for its extended afterglow. The finding of Hans Vorp has sparked intriguing conversations regarding the mechanisms that power supermassive black holes. This object acts as a cosmic time capsule, revealing details about the past and the dynamics of galaxies, and it leaves us wondering how long ionized clouds can endure after the AGN phase has ended. Astronomers have been able to piece together the history of galactic evolution by studying structures like Hans-Vorp and ionization cones, or blobs, which share characteristics with Hans-Vorp and similar ionized gas clouds. What makes Hans-Vorp so intriguing, though, is the fact that it has an unusual appearance on top of all that. The gas cloud's greenish hue and its link to the galaxy's past AGN phase make it an aesthetically pleasing and scientifically important object. The emission lines of doubly ionized oxygen give it its vivid color, which emphasizes the intricate interaction between radiation, gas, and dust in the universe. Additionally, Hans-Vorp raises questions about cosmic feedback mechanisms, specifically how these clouds of ionized gas form and what role they play. Interacting with other intriguing cosmic objects like Sagittarii US, the brightest quasar, and asterisk Hans-Vorp, we can learn more about the processes that control the expansion of supermassive black holes and how their activity affects the world around them. Known for its extreme brightness and distance, the brightest quasar demonstrates the tremendous power and activity that can. Similarly, Sagittarius A*, the supermassive black hole at the heart of our Milky Way, provides information about how black holes behave and the galaxies around them. In this light, Hans-Vorp stands out as an exceptional illustration of the interplay between these cosmic phenomena as they evolve through time. In contrast, the brightest quasar emphasizes the dynamic activity of faraway galaxies, and Sagittarius A*, shows how a supermassive black hole in our own galaxy, Hans-Vorp, continues to have an impact on it. Depicts the gas cloud that remains after such activity, illuminated by the radiation of a now-quiet galactic core. Similar to how the Fermi bubbles in the Bodi's void teach us about cosmic processes and structures, Hans-Vorp sheds light on how active galactic nuclei can shape and illuminate their surroundings. One of the most intriguing examples of this kind of supernova, SN 2006 JY, was found on September and defies the usual patterns observed in such cosmic events. In contrast to most supernovae, the extraordinary luminosity of the 18th 2016 SN 1006 JY was amplified by a dense ring of gas that encircled the star before it exploded. This gas shell that was expelled by the star in the lead-up to the supernova played a significant role in amplifying the supernova's brightness, which reached approximately 50 times that of an average supernova. What truly makes SN 2006 GY remarkable, however, is how it interacts with pre-existing circumstellar material, which greatly influences its properties. Crucial role in the bright display, the dense material around SN 2006 GY interacted with the explosion's energy, resulting in a light curve that declined in brightness more slowly than typical supernovae. This slower decline challenges simpler models of the behavior of these cosmic events. Another interesting thing about SN 2006 GY is its unusually high gamma rate emissions, which are different from other supernovae and could potentially cause gamma rays associated with. SN 2006 GY gamma ray bursts were exceptionally bright and altered the gamma ray emissions, providing a new perspective on the mechanisms driving these cosmic events. The question then becomes, how does the interaction with pre-existing material affect the brightness and gamma ray production of a supernova? The answer lies in the complex dynamics between the explosion and the surrounding gas shell. Supernova SN 2006 GY's progenitor star was a massive star with a mass estimated to be 20 to 30 times that of our Sun. Before exploding, massive stars go through a lot of changes, including shedding their outer layers and creating a dense gas shell. The star's mass loss and the subsequent interaction with the surrounding material were major factors in the supernova's extreme brightness and high energy emissions. Understanding this detailed interaction helps us understand the final stages of massive stars and how their explosions work. Spectroscopic studies have shown that SN 2006 GY can have unique emission profiles that contradict current models. By studying these patterns, scientists can better understand the physical conditions during the explosion, which improves our understanding of supernova mechanics. The discovery of SN 2006 GY has also changed the way supernovae are classified. One of the features that has prompted a reassessment of supernova classification is the presence of unusual gamma-ray emissions and interactions with circumstellar material. This reclassification is essential for enhancing the understanding and study of these powerful cosmic events. Astronomers have long been captivated by the brief but intense radio wave bursts, and FB 121,102 stands out among these bursts, earning the nickname Cosmic Repeater. Regarding its exceptional capability to release bursts of energy repeatedly, FB 1121102 stands out from the rest. However, this isn't the only thing that sets it apart. Unlike other FBS, which can display random or single bursts, FB 1121102 exhibits intricate and distinct patterns. These patterns aren't merely random. They're impacted by the environment in ways that scientists are still trying to understand. The bursts from FB 1121102 don't follow a simple repetitive rhythm, but instead occur in irregular clusters. This complexity implies that the burst production could be influenced by local conditions in the host galaxy. Another unique thing about the host galaxy of FB 1121102 is that it's located in a dwarf galaxy that's famous for its high star formation rate. This galaxy isn't your average galaxy, though. It's known for intense and rapid starbirths. The dense and dynamic environment may play a crucial role in. The mechanism behind these bursts is more complex than simple periodicity. Researchers are investigating whether these patterns are related to the specific conditions of the host galaxy, or if they're caused by extremely high levels of stellar activity, which could explain the unusual behavior of FB 1121102 and make its study all the more interesting. Influenced by other cosmic events like nearby supernova remnants or gamma-ray bursts, among other things. Interestingly, FB 1121102 may be associated with high-energy phenomena in its host galaxy. If this is the case, we could learn more about how various high-energy events interact with and impact FBS. Additionally, the presence of high-energy processes could explain why FB12 is so unusual. 11102, making it a useful object for studying the interplay of different cosmic phenomena. The dense material around FB 1121102's host galaxy may also be influencing the bursts. This material may be interacting with the radio waves to change their emission and behavior. For example, variations in the burst's observed behavior could be caused by interactions with gas and dust in the surrounding area. This feature of FB 121,102 highlights the significance of the local environment in influencing the. Investigating FB 121,102 not only improves our understanding of repeating FBS, but also provides new insights into the nature of cosmic signals. In contrast to the well-studied and understood pulsars and supernovae, FB 121,102 stands out with its intricate emission patterns and recurring bursts. These features challenge our current models and reveal gaps in our knowledge, suggesting that our current theories may require significant revision. The gamut of cosmic signals, with each new finding enhancing our understanding of the universe's behavior and the interconnections between various cosmic processes. The current investigation into FB 1211102 has the potential to uncover unexpected facets of FBS, further expanding our knowledge of these enigmatic signals and their connections to other cosmic events, such as the most powerful gamma-ray bursts, GRBs, 08319b. Gamma-ray bursts, or 319b, are the most intense phenomena in the universe. They are brief, powerful bursts of gamma rays, the most energetic type of electromagnetic radiation. The cosmic flashbulb, so called because of its unusual brightness, was detected on March 19, 2008. Understanding the extreme processes that cause these explosions will shed light on the universe's most intense phenomena. The cosmic flashbulb is a phenomenon that occurs when neutron stars collide, releasing enormous amounts of energy in a matter of seconds. It is remarkable for both its energy and its visibility, as it was the first galactic burst GRB to have an optical afterglow that was visible to the human eye. This is extremely rare considering the great distances involved. The bursts originate from a galaxy approximately 75 billion light-years away. The optical afterglow of the cosmic flashbulb was so bright that it could be detected without the use of advanced equipment. Because of this unusual visibility, astronomers were able to take detailed images and spectra, which provided rich data about the burst and its aftermath. Observations were conducted across various wavelengths, including optical X-ray and radio, which revealed a wealth of data regarding the burst's behavior and its interactions with the surrounding material. Research into the cosmic flashbulb has yielded numerous significant discoveries. The burst's energy output was far higher than that of typical supernovae and other cosmic explosions, demonstrating the tremendous power of gamma-ray bursts, and the event shed light on the conditions inside faraway galaxies, allowing for a more precise depiction of the evolution of the universe, thanks in large part to technological advancements. Research into the cosmic flashbulb has led to better instruments for observing high-energy phenomena, such as gamma-ray bursts and other cosmic events. By studying the afterglow of the burst at various wavelengths, we were able to better understand its complicated behavior. Optical observations revealed details about the light curve and spectral properties, while X-ray and radio observations provided further information. The host galaxy of the cosmic flashbulb is known for its high levels of star formation, which aligns with the expected conditions for long-duration galactic bursts. This connection helps link galactic bursts with specific types of galaxies and star-forming regions, which in turn sheds light on the broader cosmic processes at work. By studying the environment of the galactic burst, scientists gained insights into this event enhances our understanding of extreme cosmic processes and the diverse events that shape the cosmos. The power and intensity of gamma-ray bursts are vividly demonstrated by the cosmic flashbulb, which leads us to a new perspective on cosmic phenomena. Earlier discussions had focused on objects like pulses, black holes, and supernovae, but the cosmic flashbulb sheds light on the most energetic bursts in the universe. Our understanding of these mysterious cosmic phenomena has been greatly enhanced by the development of better observational tools made possible by research into the cosmic flashbulb. This has allowed us to fill in gaps in our knowledge and better comprehend the universe's most intense events, such as the discovery of the Methuselah star and the record-breaking brightness of SN 2006G. Cosmological phenomena, such as the violent deaths of massive stars and the intricate processes that govern their formation, are constantly surprising and expanding our understanding of the universe. I hope you have enjoyed this journey through space and time, and if you have, please consider subscribing to my channel. Thank you for watching.